Thank you, Kevin. Good morning, everyone. So I just realized that the first part of my title today is also the title of name of the seminar series, Produce Water Treatment and Reuse. My talk has two different topics basically, but they are related. The first one is the solar thermal desalination with combined heat and power cycle. That is basically for water treatment. And the second part of the talk would be high salinity carbonated water flooding, which is basically reuse. So drinking water supply and produce water treatment and global warming are three most pressing global challenges currently. As we all know, 70% of the world is covered by water, but unfortunately only 2.5% of it is fresh water. So even worse, like only 1% of the fresh water is easily accessible. And overall, like it is only 0.007% of water is available to feed, billions of people in the world. So that was the issue with the drinking water supply. And coming to produced water treatment, again, as we know, produced water is an unwanted byproduct of oil and gas industry. And currently we have more than 1 million actively producing oil and gas wells in the country. And almost all of them, they produce water. And on average, each barrel of oil, comes with 9.2 barrels of, this unwanted produced water. And also 97 barrels of water is also produced with each MMCF of natural gas. So in 2017, about 24 billion barrels of produced water was generated in the country. It is 70 times more in volume compared to all other liquid hazardous waste generated in the country. By far the single largest, wastewater stream is produced water. So the third global challenge is it's global warming. As again, we know CO2 is the major greenhouse gas because of its sheer volume. And I started this global warming related research like long back, 15 years ago, 2007 timeframe. So at that time, the atmospheric CO2 concentration was like around 383 ppm. And today it is like 419 ppm. And it's like a 150% rise compared to, the pre-industrial period atmospheric CO2 concentration. It was like around 280 ppm or something like that. Definitely the atmospheric CO2 concentration is rising because they're measuring it. Not very sure if it is really causing global warming or not, because it is, a debatable topic. So my work is related, basically to address all these, global challenges to some degree. So currently, we have desalination, to basically deal with the drinking water supply issue, and deep well injection, open air pits, and partial treatment and reuse of produced water are, the current practices for produced water treatment. And of course, CO2 sequestration, in saline aquifers, oil and gas reservoirs and coal bed seams are the current practices for, the CO2 global warming issue. So, basically for produced water treatment, there are multiple technologies, all of us are working on various types of them. So we basically have, thermal based technologies and then membrane based technologies. This talk is about, thermal based technologies. So one of the major issues with any thermal desalination technologies is its high energy demand. Basically, thermal desalination involves, phase change, high latent heat of vaporization. So basically, it's a very high energy intensive technology, and then, because it involves, phase change, especially, thermal desalination, the boiling is involved. In general, boiling is a very high efficient heat transfer mechanism, but unfortunately, because of some inherent, technical issues, we cannot use that high efficiency. That's an issue. So what I mean about that inefficient boiling process is that, if you look at this typical boiling curve, which is basically a plot, a log plot between delta T excess, which is here, you have a container, and where we got maybe some, produced water being, boiled. So heat is coming into the system from outside. So basically the delta T is defined as the temperature in inner wall surface temperature minus the boiling point of the liquid. So basically that is the driving force. The delta T is the driving force for the heat transfer from outside to the system. So as the driving force increases, which basically when we go this way, obviously we expect this flux, heat flux, to increase as well. So typically the boiling, is divided into 4 different regimes. We have natural convective boiling, nucleate boiling, transition, and film boiling regimes. In the natural convective boiling happens, but without bubble formation. Just natural convection is the, mechanism here. As I just said, as the delta T is increasing, the flux is increasing. It's obvious. But here in the nucleate boiling regime, the bubbles, vapor bubbles start forming on the hottest surface, which is the bottom wall of the inner bottom wall, or maybe sides also. Once vapor bubbles form, they grow with time and then detach due to the buoyancy. And when they leave the surface towards the, gas liquid interface, they agitate the liquid pool, and that agitation forces that natural convection to forced convection, and then there is a significant rise in the heat flux. You see, like here, in this regime, actually only 6 times, 5 to 30 delta T is increased, basically degrees Celsius, but we have like more than 100 times rise in the flux. This is all because of this nucleate boiling, very efficient boiling mechanism. But after that, after we reach this critical heat flux, the highest heat flux possible, the flux actually, instead of increasing, upon further increasing in the driving force, it actually dropped more than 100 times. This is because when you have more and more vapor bubbles here, before they are detached from the surface, they may actually coalesce with the neighboring bubbles and form a continuous vapor layer. As we know, the vapor is a bad conductor. Further heating is like not as efficient as before. To come to the highest heat flux again, which we got it at around 30 degrees delta T, or 130 degrees Celsius, we have to heat the container now to more than 1,000 degrees, to come to the same level. So it is all sheer waste of energy, very inefficient, not safe, because some of the containers may actually melt, at these high temperatures. Basically, one of our objectives in this work is to deal with that, issue that has been there for, more than 90 years. So our approach to basically handle that, film boiling and transition boiling regimes is like this. See here, what we are trying to do here is basically, what we have here is basically, this is a small glass vial filled with degassed, here in this case, DI water. And, it's a glass surface inherently hydrophilic. We have immersed another rod, glass rod, but it is made hydrophobic. This glass rod is just inside the liquid and not touching the container. And the idea is basically, to prevent the bubble formation on this hottest surface, bottom inner surface, and promote them on the coldest, the surface. So if we can do that, so we are in the nucleate boiling regime, but at the same time, we don't have any resistance formed on the heat transfer pathway. So that was the hypothesis initially, but it is proved correct, right? As you could see, no bubbles are formed here, the hottest surface, but all of them are formed here. And then it's boiling right there. No bubbles are forming like at any other place. So we tested this hypothesis, in various, schemes. In the second, system, instead of that rod, we have a glass bead floating on the surface of the liquid. The glass bead is actually heavier than the water, but because of its hydrophobicity, it is still able to float. So again, the idea is same. We heat the while here, but we expect the bubbles to form on that bead. It's again happening. Bubbles are forming here. A lot of boiling happened here from here to here. Bubbles are only forming there. So finally, we have another way of testing the same hypothesis. In this case, what we did is, initially we did not have that hydrophobic rod. We just heated the liquid to its boiling temperature and preventing the formation of the bubbles by making the container hydrophilic. But if we keep on doing it, we are going to be in the natural convective boiling regime, not very efficient. At the same time, the liquid will be superheated, and then there will be a flash suddenly. So we don't want that. So then once the liquid reaches to the boiling temperature, we inserted our magic rod. Upon insertion, as you could see, a very vigorous bubble nucleation is happening only on that inserted rod. So we wanted to use this new way of, potentially more efficient boiling technique for our solar thermal desalination, basically. So this is a schematic of the technology that we are proposing. We have a boiler here, two boilers basically. This is the one boiler and the second boiler, and we have two cycles here: the outer cycle and the inner cycle. In the outer cycle, this is just a pure distilled water. It is becoming steam, using the solar radiation, basically. I'm not going to go into the details of the design. It has a double wall, and the inside wall is basically, coated with some solar absorber material. And there is a vacuum between these two layers, so that, all that heat generated is just going to go only to that water. So once the steam is generated, the steam is used to run a turbine. The turbine in turns runs the compressor. A compressor. The saturated water, is very hot here, and it is condensed, with the incoming salt water or produced water. Basically, the water, which, the condensed water is basically pure distilled water, is actually going into this again. This is in this system outer loop. The water, the dirty water that is going into the second boiler, is basically boiled in the same way, but at a reduced pressure because of this compressor. And then we have distilled water generated here again, and that is taken out as the product. And we have concentrated brine going out, this has to be disposed of, but compared to the volume of the feed, the concentrated brine is going to be, less in volume. So, all right. So we generated, high salinity, produced water in the previous step. Again, that has to be treated or maybe reused. We chose to actually reuse it for enhanced oil recovery applications. However, the issue with using that very high salinity water for enhanced oil recovery is that it's not going to work. We have something called low salinity water flooding technique, for enhanced oil recovery. But to use that technique, we have to dilute our concentrated brine that we produced or maybe obtained directly from a field with some fresh water. So again, that's not a good thing, right? So we wanted to use that high salinity produced water as it is without further diluting it. I'll tell you how. I'll show you how. So this is our microfluidics facility in our lab. So we ran some microfluidics based enhanced oil recovery experiments. And I'll tell you like what is happening here. This is a small microfluidic chip. You got the dimensions here. So what you're seeing here is like two things, like the pore space, which is the blue space here, and the light blue is the grain space. It is like a rock, these are grains, and this is just pore space. Right now, the pore space is filled with 100% water. So let us look at it in a zoom in view. So the same thing, the same chip, but it is in zoom in view. These are the grains, and this is the water. This is how reservoirs are there, like before oil and gas actually forms somewhere else and migrates into this particular reservoir. We are basically trying to simulate an oil reservoir in the lab. So then we injected oil, which is shown in red here, until no more water is produced, meaning that all this blue left over is still water, that cannot be reduced further. And the red is oil. The water is called as reducible water, and the oil is called as, initial oil saturation. So let us actually zoom it in again. So this is how the pore space is occupied by oil and water. As I said, these are the sand grains. And then we injected water to displace this oil to basically simulate water flooding process. So, some of that oil which was there was displaced by water. And the remaining oil that you are seeing here is irreducible oil, basically remaining oil saturation. It cannot be reduced further. Let us zoom it in again to see like how it is different from the previous step. So as you could see, oil droplets, oil became droplets. Previously, oil was continuous phase. And even this big blob of oil is also discontinuous phase now. And any more injection of water, which is continuous phase, is not going to be useful, because the injected water is going to be coming out without actually affecting any oil saturation. So basically, whatever we do after this, is called as to recover some more of this oil is called as enhanced oil recovery. We use low salinity water flooding. We can use we can inject some low salinity water to basically, move some of this immobile oil, or we can inject CO2 and many other things, surfactants, polymers, and so on. So in this case, we injected methane gas. to try to get some more oil out, there is a third fluid here. Let me zoom it in to see. And here we have three fluids: oil, water, and gas, methane. Because of the presence of methane in the pores, and of course, some of that oil, which was not coming out previously, had to come out. It came out, basically. So, basically methane was displacing some more oil. If we inject CO2, carbon dioxide, in the place of methane, the similar thing will happen. And the oil is coming out, oil will come out, and then this injected CO2 stays there, meaning that we are getting the carbon sequestration and also the enhanced oil recovery at the same time. So what we are proposing is, to use high salinity water as it is, right? You see, like how, why high salinity water is not useful for enhanced oil recovery in this microfluidics experiment. What you're seeing here is a channel, 100 micron channel of 500 micron channel of a calcite coated glass surface. Basically, this is. So initially that channel is filled with high salinity brine, 5 molar sodium chloride solution, followed by a model oil, acid number 1.5 model oil. And so initially the water was displaced, high salinity brine was displaced by oil, and then the water was re-injected to displace the oil, basically to simulate again the water flooding step. But as you could see, even though it is just a straight channel, there are no pore networks, still a big blob of oil is stuck to the surface. And when we were injecting this NaCl, this is non-responsive. It was not moving. I have a small video, I'll play it. But when this water, this high salinity brine, is replaced by a relatively low salinity brine, you will see what happens. So right now, the 5 molar NaCl is being flooded to basically try to move that oil blob. Nothing is happening. But when it is replaced by that 0.164 molar sodium sulfate solution, it started moving. The previously stuck oil is getting released. Just focus on the oil droplet. It's still the flooding is being it's continued. Yeah, now the low salinity water flooding is stopped. But even after the flow is stopped, you will see the response of the droplet. That is the effect of low salinity water flooding in the reservoir, basically. As you just have seen, so high salinity water is kind of useless for enhanced oil recovery purpose. We have to actually dilute it with some fresh water, which we don't want to do. Instead, what we are proposing and doing is that saturate that high salinity brine with carbon dioxide and make that salt water soda, and then use that liquid, high salinity carbonated water, for enhanced oil recovery, with the expectation that we will get rid of the produced water, high salinity produced water, basically injected into the reservoir. Simultaneously, CO2 is being sequestered and oil is coming out. Three things are happening at the same time. Two bad fluids are being sequestered, and one, I would say, maybe being a petroleum engineer, a good fluid, oil, is coming out. So basically, that was the reuse thing that we are doing. And I would like to end this presentation with this acknowledgement of the funding agencies, OSU, BHG, ACSPRF, Nitrolip Technologies LLC, ADNOC, and NSF EPSCoR, and USBR. And the graduate students, Sushobhan Pradhan, he is actually defending his PhD dissertation today. And Dr. Imran Sheikh and LONO, he will be defending his MS thesis next week. And of course, my co-investigators, Dr. Khalid Salam for the solar desalination project, and Dr. Clint HL for the high salinity produced water project. So I am open for any questions.
Great, thank you, Prem. Appreciate the presentation. We do have a couple of minutes for questions, so you can put those in chat or raise your hand. A question I do have is about the solar thermal treatment that you have proposed.
Yes.
Have you built and tested that at small scale? I saw the testing you've done with the boiling, but have you constructed that?
We haven't actually. We are going to construct it as a part of the USPR project that we have right now.
Gotcha.
So that's in the plan.
Excellent. Very good. There are other questions? Oh, Hassan?
Yes, good question on your efficiency for the solar system. You mentioned that your concentrated brine was little compared to the slime water. Now, typically, evaporation system is not very efficient systems. And the design that you've done, you mentioned it seems to be efficient, but it didn't provide any information about efficiencies or let's say techno-economic analysis in addition to what was your recovery out of that saline water. Could you talk about that?
Sure, definitely. I mean, as I said, the solar thermal desalination has some, technical advantage over, RO-based, technologies because, we don't need membranes and we don't need to deal with, pre-treatment or, membrane plugging and so on. But as I said, the issue is the high energy demand, right? So here, we are not providing any, electricity or something like that for boiling. Basically, we are depending upon the solar radiation. Of course, at the end of the day, we will have concentrators, basically, in our final designs to concentrate the solar radiation. And we are also working on some plasmonic nanoparticles, basically to capture near 100% of the solar radiation and convert that into heat. It's a very high efficiency solar, collectors. Our colleagues like Khan Kalkan and Mary Andieppen are working on that technology. We are going to be integrating our design with their plasmonic nanoparticles, basically to make it very highly efficient. And they tested their nanoparticles for solar collector application, and they found that they can actually go up to 500-600 degrees Celsius. Currently, we are our coatings are like commercially available, solar coatings. They are going only to 100-105 degrees Celsius, not good enough. So we are trying to develop better solar collector coatings. And overall efficiency, how much, energy point of view, no clue as of now, because we are still working on it. But the idea is basically, to use this, so-called free solar energy, and also recycle it very efficiently using this combined heat and power cycle. We would expect it to be a very highly efficient system overall, if everything goes well at the end of the day.
Okay, well, thanks for this. I was hoping that also you talk about possibly estimated efficiency that you would like to get to based on the current technology in solar cells and your compression, your turbine, and so on. but that's something still ongoing, right?
Yeah, sure, sure.
Okay,
It's
sounds
ongoing.
good. Thank you.
Well, thank you for the questions. Prem, there's one in the chat, but we need to move on to the next presentation. So you might respond in chat to.
There is a question. If there is 1 minute, maybe I can quickly answer, Kevin. So have you considered making the container itself hydrophobic? So if we make the container itself hydrophobic, the problem is going to become worst. We wanted to prevent the bubble formation on the heating path. It would actually make it, more bubbles on the container, which is not going to be a good thing. Of course, we consider, but it is going to be a bad thing. So.
All right. Well, thank you, Prem.